So we just did a couple of videos about acids. Let's calculate the pH from a base concentration. So for a strong base, it ionizes completely. So if I had a zero point 0.1 molar solution of sodium hydroxide, in solution, my hydroxide concentration would be 0.10. I also have like a warning here to watch for stoichiometry. I'll put a couple other little caveats in here. Right, if I'm asking you for the OH minus concentration to think about pH, I give you calcium hydroxide. If it's a zero point 0.1 molar concentration of calcium hydroxide, because in calcium hydroxide you get one calcium and two hydroxides, this means the OH minus concentration would be zero point 0.2 molar. So this is hugely important to watch out for the stoichiometry. The other thing, if you are kind of putting together that we're going to get really cumulative, I mean, calcium hydroxide is not super soluble. So we will deal with weak bases, but I would not count calcium hydroxide as a weak base um, because it's not just the ionization part of acting like a base, it's a solubility issue. The short answer is if I give you something like calcium hydroxide, recognize it as a strong base because it has OH minus in it. That is the key to recognizing strong bases. They have OH in the formula and they will kick that OH minus out as is. It doesn't have to do anything else. If I'm giving you this, you can kind of ignore the solubility factor here. We will deal with slightly soluble things in a later section though. Now, okay, we still haven't calculated. I have an OH minus concentration from my base. I have two paths that I can take to calculate the pH. I do not care which one you do. One, I think, tends to be easier, but it is entirely up to you. It comes with its own pitfalls. So option one, we're going from OH minus concentration, find the pH. You could calculate the pOH. So you have the OH minus, you could take the negative log of it, and then use pH plus pOH equals 14 to convert that to a pH. That's one way. This is probably the fastest math way, but it's also the easiest way to forget that you still need to make a pH and accidentally report the pOH. The other option is that you could take your OH minus concentration, use KW to convert this to an H plus concentration, and then take the negative log of that value. It's entirely up to you. I do not care which one you do. So those are strong bases. For a weak base, it is exactly like we had with weak acids. You will do an equilibrium. So we know that it doesn't 100% ionize, and by ionize with these weak bases, I mean react with water and produce OH minus like a base does. So you will have an equilibrium constant value. But now, really, as you can see within this problem, if we're finding the pH of a zero point 0.1 molar solution of ammonia, we're given a K value, but it's a Kb. And it's because it is the equilibrium constant for this molecule we are looking at acting like a base. So the Kb for ammonia is 1.76 times 10 to the minus fifth. If I want to calculate the pH of this, I mean, I need something at equilibrium. And I mean, pH implies I need an H plus at equilibrium. But if I put NH3 in solution, it's going to react with water to produce NH4 plus and OH minus. The OH minus it produces is why this solution is basic. So I'm going to start by finding the OH minus concentration at equilibrium, and then you can choose whichever path you want to go down to find the pH. So I have my reaction that I just described. Initial conditions are 0.1 molar NH3, no NH4 plus, no OH minus to start. And right, I have to show this reacting with water to do the reaction, but water's a liquid. It doesn't show up in my equilibrium constant expression, so I'm just going to cross out this whole column. My reaction has to move to the right. I lose 1x of the reactant, make 1x of each product. My Kb expression, still just an equilibrium constant expression for the reaction as written, NH4 plus times OH minus over NH3. There's no water in here because it's a pure liquid. So I have this expression to plug my equilibrium rho values into, so x squared over 0.1 minus x, and I have the equilibrium constant value. So that's equal to 1.76 times 10 to the minus fifth. And I'm going to assume that x is small. All right, I've got 0.1, so 1 times 10 to the minus 1 versus 1 times 10 to the minus fifth. It's more than 10 to the third apart. Let's try assuming that x is small and see if we can make this algebra any faster. So when I do this, I get x is equal to 1.33 times 10 to the minus third. If I test it, so I take that x, divide by 0.1, multiply by 100, I get 1.32%. So that was a great assumption, assuming that x was small in this case. And now that x value is my OH minus concentration. So I've got side-by-side solutions for you here so that you can see them both, right? Option 1 where you find the POH and then convert it to a pH. Option 2 where you find a concentration of H plus and then convert that to a pH. Either one, as you can see, they both give a pH of 11.12, which should sound correct to you because this is a basic solution. So we had a weak base in solution. We need to get a basic pH for our answer.